One of the most important discoveries of the late 19th century occurred when George Ohm determined the relationship between potential difference and current for metallic conductors. This session revolves around the work that Ohm did over 100 years ago and focuses on practical work that can be done in any classroom.
So what is Ohm's law? We can say R is V over I, or we can say V is R times I, or I is V over R. Let's concentrate on this one. What does it say? It says the voltage across a resistor divided by the current gives the resistance. But there is a danger here. There's a pitfall, because one could say, well, this is a definition of resistance. We can always work out V over I and we get a R. That then is not a law or a rule. So what is then Ohm's law? The important thing is that the ratio of voltage divided by the current for a lot of conductors is a constant. And hence the important thing here is that V is a constant times I. And that means that I is proportional to V, V is proportional to I.
At ZamaZulu, the teacher introduces a practical lesson to demonstrate Ohm's law. The outcomes of this lesson for the learners are to connect simple DC circuits, to use Ohm's law to perform simple calculations, to read an ammeter, a voltmeter, and to use a multimeter, to perform an experiment to demonstrate Ohm's law for metallic conductors. The teacher begins the lesson by revising Ohm's law.
In this equation, what does V stand for?
V stands for potential difference.
Potential difference measured in volts. I in that equation stands for what?
For current.
It stands for current. It's measured in?
It's measured in amps.
In amps or amperes. R in that equation stands for what?
R stands for resistance.
Right. Now, Ohm, after doing a series of practical work and experiments, found that current is directly proportional to potential difference. And in our first investigation, that is what we're going to be showing. You can see that when you raise potential difference, you're actually raising current as well.
Learners are given a worksheet showing a diagram of a circuit which they must set up using the available resources, that is 4 leads, 1 ohm and 3 ohm resistors, a long piece of resistance wire, ammeter, multimeter, press stick, paper clips and a battery pack.
Traditionally, the main role of practical work was simply just to confirm the theory. And that is how a lot of teachers have approached it. And any other learning that took place, or the development of skills that took place, was more incidental and wasn't really the focus. With the new outcomes-based curriculum, though, the focus should be on the development of practical skills, as well as a little bit of an aspect of confirming theory, but the emphasis should be more on practical skills.
One of the educational outcomes that the educator is trying to achieve is to allow learners time to develop their process skills through practical experiments.
We also wanted them to be able to work with the apparatus of a circuit. We wanted them to be able to record their data. We also wanted them to be able to draw a graph based on the recorded data.
As learners conduct the experiment, the teacher observes the different groups. He notices that learners are battling to follow the circuit diagram.
In our school, we don't really have as much equipment as we would like to have. So you would find that most of the time, practical lessons are done by me as a teacher having to stand in front and demonstrate. And so they don't really get a chance to manipulate the apparatus and work with the apparatus themselves.
To overcome this problem, the teacher carefully demonstrates the setting up procedure.
Take one wire, connect it into your battery. You've got a 6 volts battery, right? Take one end of that wire and connect it to one end of the resistance, right? Take another wire, you connect it onto the second end of the resistance and connect the other end of that wire to what? To the ammeter, right? Third wire is going to start from the second end of the ammeter to the battery, like that. You've got the reading already. It's an indication that there is current now flowing in the circuit. You have now put together.
This reading is taken for different numbers of batteries.
Look at the current now. It was 0,2. It has moved up slightly. It's in between 0,2 and 0,4, right? Now let's look at the potential difference now across the resistance. It is now 1,94, right? The voltmeter, right?
The teacher will also demonstrate taking the potential difference across the resistors with different numbers of batteries.
If it shows negative, it means you must swap your wires like this. Put one over there and put that over there. It's 3,6.
With practice, the learners are able to do it for themselves.
0,8.
8, I think.
So for 3 cells, it's 0,6. Yeah.
0,6.
We wanted them to work as a group, to share ideas, and not so much an individual effort, and not so much me as a teacher standing in front and actually delivering information. We wanted them to actually find out things on their own as a group.
We're gonna first take the 4 cells and we must put the paper clips between the cells so it can be one cell. You want to take this black wire and connect it to the resistance. So the resistors connected to the ammeter, and here to the ammeter, the red wire. And you got something which looks like this. So you connect again to the cells. This is the reading that we got on the ammeter. This is 0,8. This is the reading on the voltmeter. It's 4,89.
The teacher explains that the measurements need to be tabulated.
On this space, write the voltage that you got when there was 1 cell, the voltage that you got when there were 2 cells, 3 cells, and 4 cells. And on the other side, you write the current that you took when there was 1 cell, the current you took when there were 2 cells, 3 cells, and 4 cells.
Learners take measurements using different numbers of batteries.
We've got all the answers.
Then from those readings, you use the graph papers that we've given you to plot a graph of potential difference versus current. And please do use a scale.
One of the biggest problems that learners face with graphs is finding the correct scale.
We found that they were not able to come up with scales that were going to give them graphs. They just assumed that they would actually plot the points as they were without actually using a scale. So it's something that we really need to relook and actually make sure that we teach them the usage of a scale. 2.14.
Learners have certain misconceptions when drawing graphs.
There are a number of mistakes that learners make when they draw graphs, especially if they draw graphs from scientific data that they've collected. The first and probably the most obvious one to anyone looking at a graph will be that they make big blobs for points where they should really make, and that's just really a technique thing. And the other thing, of course, is that they sort of join the dots on the graph paper, much like a rainfall chart, whereas with a scientific graph, what should actually happen is they should draw in a best fit curve, a line that best represents the dots that they've made or the points that they've actually plotted on the graph paper.
There are also problems relating to drawing this specific graph.
On this side, and then we put a potential difference on this side.
Here, the learner is making an error often made by learners and teachers alike. Potential difference is an independent variable and so should be represented on the horizontal axis, not the vertical axis. Current as a dependent variable should be represented on the vertical axis.
So this is our table. It's 3,52 and 0.5.
You were supposed to have a straight line. Obviously, some of the points will have fallen outside a straight line. And what does this straight line actually tell us about the relationship between current and potential difference?
When you increase the potential difference, you are also increasing the current.
When you double potential difference, no matter how much amount you had, if you double that, right, you will actually be doing what to the current as well? You will be doubling it, right? If you triple potential difference, you'll also be tripling current as well, right?
In this practical lesson, the learners have reached their outcomes of connecting simple DC circuits using Ohm's law to perform simple calculations, reading an ammeter, a voltmeter, and a multimeter, performing an experiment to demonstrate Ohm's law for metallic conductors.
Because you know, a bunch of words stating Ohm's law is easy to forget, but when you actually do it practically, and it's quite another story.
Hello everyone, we have just seen the video, and on the studio today we have Dale, we have Andrew, and we have Lolo. We are going to be chatting about the lesson that we have just observed. The teacher started off by linking the previous lesson to the new lesson that he was teaching. How do you feel about the strategy of introducing a lesson in a class? Would you like to comment, Lolo?
By always studying from the known to the unknown, it makes things easier for the teacher as well as for the learners, because that's how you get them involved.
I think it was a good idea to start with questions.
Yes.
It gets your learners thinking at the beginning of a lesson.
Yeah, so he did use questions in order to link the previous lesson with the new lesson. And then from there, then he had to deal with the scientific language. We have seen here the terminology, where he had to use cells, batteries, etc. We have seen the scientific laws. He talked about the Ohm's law. We have seen the scientific symbols and formula RV/I. How do you think that should be best taught in the classroom?
I mean, he used those, these are scientific words, you know. They're concepts, they're not just words. And they have sometimes very different meanings from the meanings that they have in everyday language. And I think just as educators, we need to take cognizance of that. That learners are not coming in again as blank slates. You know, they're coming in with misconceptions, alternative conceptions, it's perhaps more correct. And so we need to find out where they are, and we need to use that as a stepping stone to introduce new knowledge, to build up on that, to deal with misconceptions and so on. So I think the teacher somewhat showed some sensitivity towards that. But I think a lot more should be done in the classroom by educators, you know, to make the link between the way we use language in everyday language and how we use it in science, and also how we use it in different branches of science, if you like, or different subject areas. You know, we have the cell in biology.
Yes.
What are they bringing from the cell in biology? How are they going to confuse? You know, they've just had a lesson with teacher X who's just been hammering them about the cell and the different parts of the cell, the mitochondria, the nucleus, and what have you. Now they're walking into a physics class and we continue to talk about cells. You know, are we taking cognizance of that, is my question. And if we are, how are we using it? We need to use it more positively. We need to make reference to these things. We need to clarify things so that learners can develop along a trajectory which is, you know, going to enhance their appreciation and profound understanding of these scientific concepts.
Do you think it's an easy task to do that as a teacher in a class?
I think you've just got to be continually aware of it. And every time you use a scientific word for the first time, talk about how it gets used in everyday English. And the obvious one here is that at home we call the things batteries, and in the science lab we call them cells.
That's right.
And as long as teachers make learners aware, that learners actually cope quite easily with it.
And when do you bring in the whole idea of formula and things in the whole lesson?
Yes, I
the
mean,
formula, the V and the R, etc., the resistors, when they have been using the wires, etc., the bulbs.
Yes, I mean, I would only introduce those kind of symbols and so on at the abstract stage. Now you have to start from the concrete and develop to the abstract, you know. And therefore, I would say, you know, in getting to the point where one is talking about V is equal to IR or V, you know, whatever you talk about, in fact, for that matter, in terms of symbols, that you need to be certain that some of the basic concepts have been grasped. those are symbols that represent concepts that are very powerful concepts in scientific terms. But have they actually been established? And in order for them to be established, you need to start with from a concrete base. You know, so I would have learners appreciate the relationship between potential difference and current, and how those two relate in terms of doing practical things. And in fact, if that has been done, remind learners of that, and actually start from that as an initial point, and then develop further, and actually do experiments, and then eventually come to a point where I say, well, what we actually mean in summary of all this is just a way of summarizing and working with things. Because, and then also I think we need to make learners aware that there's mathematics comes in as a very powerful tool. And if we work with symbols, then we can work things out mathematically. We can do calculations, we can solve very complex problems when we are working at the abstract level. But we need to start from the concrete.
I also think that this lesson really helped in that the learners weren't just talking about potential difference in current as abstract quantities. They were real things, that they had measurements for them. The numbers hadn't just come out of a textbook somewhere. They'd actually got them from their circuits. So I think that really helps as well.
Absolutely, yes.
So teaching science is actually confirming theories. And how do you think that has been done in this field? How has the teacher confirmed the theories that we're talking about?
The teacher started explaining, but that was not enough. He went on to demonstrate to the learners what was happening or what this theory was all about, and was also involved in a practical work where learners were manipulating the apparatus to confirm what was said before.
And what advice would you give to a teacher who have limited resources when teaching this lesson?
Limited resources.
Yes.
Well, that's a tricky one. I mean, demonstrations is one thing that we always fall back on, isn't it now, Tembi? When you're in a situation where you have a huge group of learners, and you only have one circuit board and a few wires here and there,
and maybe
some
two
cells,
bulbs,
bulbs and what have you. You know, it's a big challenge. You're not going to get the 100%. You're not going to get what is ideal. But, you know, I think educators and all of us need to be creative about how we use limited resources. Demonstration is definitely one of them. I have been in a situation very recently where a teacher dealt with limited resources in many very different creative ways. And one of the ways that they did was they asked the learners, individual learners, to come after school to work with the equipment. So different learners came at different times. Some came during break time. It's a very it's not an ideal situation, but it's a way of overcoming a real obstacle in order to get learners to actually work with the equipment, actually develop the concepts.
And one of the things that the teachers did in the video was to give the learners an ammeter to find the readings. How do you think that was done in this case?
I think that learners have a lot of difficulty with an analog scale where you've got a whole lot of numbers and then there's a needle that moves across. It's very easy with a digital scale, they've just got to write down the numbers. But what I find, even among tertiary students, is that because they don't have a good understanding of a number line, you know, if this is 0 here and this is 5, well, where's 3 in between? Or if this is 0 and this is 0.1, where does 0.02 come in, or whatever. And they need that both for plotting the graph and for reading the meter. It's quite nice that both of those skills came in the same lesson. But maybe the teacher needs to be aware that that's a difficulty and check perhaps on a large drawing of an ammeter beforehand that learners can actually know what they're doing. Those ammeters are particularly complicated because there are 3 scales and the learners have to choose which scale they need to read off.
I think with time, just as Dale said, Tembi, one of the misconceptions, I'll call it that, with respect, is basically being that that OBE means that learners are not to be assisted with these things, you know. And people think, well, give them the apparatus, give them the meters, give them everything, and they will discover Ohm's law all over again, reinvent the wheel. You know, that is I think a serious misconception. And we didn't see it happening in this case because the teacher went about also talking to the learners, showing them how to do the connections, you know, so that they were then confident to actually do these things themselves. But absolutely sure, I mean, what Dale mentioned is quite important. You know, the scale is very difficult. We need to appreciate that, and we need to help assist the learners.
Do you think that maybe the maths teacher should work together with the science teacher
I think so, yes.
in helping the learners in
Yes.
learning the number line and things like that?
Yes, I think we need departmental meetings. We need more departmental meetings where people are sitting and not just having a cup of tea, which is not a problem, but where people are actually sitting down and looking at how they can integrate these things, how the teachers can work together, how they can maybe even do team teaching, you know, and what are the overlapping problems and how they can deal with them as a team. You know, we definitely need those kind of meetings to take place where people are actually looking at the problems, looking at the resolutions, looking at actions and who does what and when those things are going to happen. And then I think we'll see more of an integration between maths and science, because the two really are intertwined. You know? You can't have maths without science, you can't have science without maths.
I also think it's useful for the science teacher to know when concepts are being taught in maths, like graphs, and then to make a point of actually using those concepts soon afterwards, so that learners can see the connections as well, and they don't leave their science downstairs when they go upstairs to maths.
You're bringing in a very important point of graphs. Plotting graphs and interpreting graphs is a very big problem in our schools. How would you try and solve those problems in the classroom? Plotting and interpretation of graphs by learners.
Yeah, I think the first part is that the teacher needs to appreciate that learners do find it difficult, and maybe to start with situations where the teacher has chosen the scale and the learner just has to plot the values, and then to assist them perhaps in groups to be choosing scales for values that the teacher gives, and to work up to it stepwise.
Because in some cases I've seen learners plotting graphs, putting some big balls. They'll put a point and then around that point they'll put a big ball. And many other things.
Yes.
So maybe that's the way in which you can help the teachers. Any other thing?
Something which was mentioned on the video, the fact that we plot V against I, you know, and then get a straight line graph, and then we go, well, R is equal to V over I, which is all okay and cozy, except that we're introducing a very serious misconception. And as I said, it was captured in the video. But I think we need to drive the point home, because this is still common practice out there, and learners go away thinking they're, you know, very confused. One, two, reinforcing the misconceptions that come out related to current and potential difference.
I also saw on the video that learners were given some worksheets, and they had worksheets in front of them, but the teacher kept on reading for them as well. Do you think it's a good idea to do that?
I think all teachers experience the frustration that you give learners this beautiful worksheet and they just don't read it. Yeah, it's a reality that they skip over things and maybe just look at the diagrams. But I don't think that doing it for the learners is the solution to that. Perhaps there needs to be some time given at the beginning of the lesson where everybody has time to read it silently without interruption.
And so your suggestion is that maybe the teacher should give the learners some few minutes to read through the worksheet, and after reading through the worksheet, then do the experiment. Because in most cases, what they do is they actually look at the diagram, and then they do the diagram, and then when they're stuck, then they start reading.
Which is human.
Yeah,
which is human.
Yes. Thank you very much, Dale. Thank you, Andrew. Thank you, Lolo. Viewers at home, that's all we have for today. Thank you. Bye-bye.